Hey guys, today we're going to be going over the Fourier Transform from an audio programmer's perspective. I'm going to be using Desmos to help visualize what the Fourier Transform is doing. And hopefully you get this at least as good as I do, because it took me a while to really wrap my head around it. There's some great resources online though. Three Blue, One Brown did a couple good videos on the Fourier Transform. This is a little bit different than both of those, but let's go ahead and get started. So basically, we're starting out with a basic sine wave with a frequency of 2 and a phase shift of 0, which I will change later, and we'll see why that's important. But here is the graph for it. It's just sine of 2 pi times the frequency times x plus phi, the phase. And I'm only graphing from 0 to 2 for the sake of this. I don't think you need to see the whole graph. So basically what the Fourier transform is doing is it's taking this wave. This is our sample wave. I'll refer to it as. And we are going to create our own sine waves to compare to this wave. We're going to be testing the waves we make with this wave. And we're going to see if they align. And if they align, what's going to happen is the sum of the product of all the points is going to be relatively significantly higher than if the waves don't align. And I'll go ahead and give an example of that right now. So here's just a simple sine of 2 pi wx, w, which I'm trying to make omega, which is really our sampling frequency. And so I'll graph this. Right now it's 1. And as you can see, they don't align very well. But as I get closer to 2, obviously they start to align until they align perfectly when w is 2. Or omega. I'll try to say omega if I say w. I'm sorry, it's just the limitation of Desmos. So as you can see, when they're perfectly aligned, actually the product of all the points is always going to be positive. And here's a little look at that. This is just graphing the product of all the points. And as you can see, it's all positive. So again, this is going to be a relatively significantly higher number than if our frequency, our sampling frequency, does not match the actual frequency, right? So if I go down here, we're going to get a lot more negative numbers, as you can see. And it's going to start canceling out and oscillating around 0. And I've done this here by taking the integral from 0 to 2. And as you can see, this number is fairly close to 0 for pretty much any value until I get close to 2. And as you can see, as I get close to 2, it goes to 1. And then everything else goes down, and then it stays towards 0. And so that is kind of the basic premise of the Fourier transform. But there's still more to it than that. And it's going to come back to the phase. So basically, let me go back to where the waves align perfectly, right? So this is where both the sample wave and our wave that we are sampling with sample frequency 2 are aligned. And very clearly, again, this integral is equal to 1, that pretty much the highest value, significantly out of all points, because it aligns perfectly. But let's look at the cosine wave. The cosine wave is off because it's phase shifted. A cosine wave is a sine wave that is just phase shifted. So as you can see, if I do the same thing with a cosine wave, and again, I'll plot the points for that. When I plot the product of all the points, look at that. It perfectly oscillates around 0, which is an issue because the integral now from 0 to 2 is going to be 0. So although the frequency matches, our sampling frequency of 2 is the same as the actual frequency of 2, because of the phase shift, we're actually going to find that the sum is 0. And you can think about it as if I phase shifted the initial wave with sine. Then we would run into the same issue. So whenever there would be a phase shift of pi over 2, we would see that with the sine. Of course, it just happens to happen with the cosine with the sine wave. And so this issue is the reason why for the Fourier transform, we use both the sine and cosine waves to test to see if the frequency is there. Because if I now take the magnitude, regardless of the phase, whenever omega is 2, which is our sampling frequency, we're going to get 1. So now, if I just show, let's see, both of these waves, right, the sine and the cosine. Now, if I change phi, which is the phase of the initial wave, yeah, the integrals change for the sine and cosine waves themselves. And again, these represent just sort of the presence of a cosine and a sine wave. But regardless of what I change, sorry, not W, or omega, regardless of what I change phi to, the integral, or the magnitude, rather, of both of those is going to be 1. And that's because of the identity sine squared plus cosine squared is equal to 1. And so this helps us identify frequencies regardless of phase, which is super important because any input sample wave could be any phase. And so that needs to be something that can't stop us from doing frequency analysis or spectral analysis. And so this is really the foundation of the Fourier transform, taking advantage of the identity sine squared plus cosine squared is 1, which is really just helping us eliminate any phase issues, because there is, whenever the phase is whatever it is, it's going to change the value of the sum of our sample wave times the wave we're sampling. So yeah, the phase does actually influence the presence of a sine or cosine wave, but again, because of the identity cosine squared plus sine squared is 1, we'll still know what frequencies are present based on that. And now again, if I change omega, our sampling frequency, it's also clear that when it's non-zero, or when the frequencies don't match, that this value tends towards 0. But when I get to 2, again, it just goes to 1, which is relatively the highest value, which indicates the presence of the frequency 2 in this wave. So we have the frequency of the sample wave. Like, this is unknown when we're sampling, but for the sake of constructing it, of constructing something to sample, we're going to have a frequency and a phase. So here is our wave, here, the same thing that we've been doing. And then now we have a sampling frequency. And then again, we're going to sample the cosine and the sine components of this wave. And so again, we do that by taking the product of the sample wave and the wave that we are using to sample frequencies at, which I'm calling frequency of S in this case. But if I use this parameter W just to show, then I can graph what the product of these waves look like. And here you can see some frequency modulation going on, which kind of looks cool. But this is essentially what the product looks like for this particular wave, with a frequency of 2 and a sampling frequency currently of 6.6. So if I go to 2, then you can see it becomes like a standing wave, just a basic wave. And as you can see, both of them do. And now again, we can take the integral of these waves and then the magnitude, and then this magnitude is going to be high when the frequencies align, and when the frequencies don't align, so my sampling frequency is off, the value is going to be significantly closer to 0. Now note that I'm actually going to 10 here in this integral, which is basically a longer sampling period, which means more samples, which means we're going to get a much more accurate result, and everything else is going to be a lot closer to 0. And ideally, we would like to have a large enough range so that we can clearly identify frequencies. And so then here I'm just plotting the Fourier transform. Basically, I'm using a discrete version of it, a discrete Fourier transform, because the Fourier transform itself is a little bit too computationally expensive for Desmos, which is something I would really like to see them work on. But I'm going to go ahead and hide these waves. Here's the initial frequency. Again, we have a frequency of 2, and right now a phase of 0. And I'm going to plot the Fourier transform again, and I've scaled it by 10. So basically that means that it's going to show that there's a peak at 0.2, which means the frequency is at 0.2, but really it's at 2. I've just sent 10 times the input in so we can fit it comfortably in the view. And again, if I change this phase, nothing here is going to change. Well, actually you see that there's a little bit of change, but it's still going to clearly identify that there is a frequency present at 2. So a lot of this you went over, but again, here's an example, and I'm using, here are the Fourier transforms. Again, it's just the sum of all values of the sample wave and the product, well, the sum of that and the product of the cosine and sine waves. And just to reiterate again, the reason we use both cosine and sine waves is because we can, once we have two different waves of different phases, then we can get rid of special cases when the waves cancel out. And so this thing I've let load for a while, but this is what the graph of the Fourier transform actually looks like for a frequency of 3, and I've done the same scaling mechanism where it shows at 0.3. And as you can see, there is quite a big peak there. And there's some mess over here, but don't worry about that, because whenever you're looking at this, it'll be pretty clear that there's a peak at 3. This takes a while to plot, so that's why I didn't plot it earlier, or in the other one. Alright, so now we need to talk about the discrete Fourier transform, because this is what we ultimately want to implement. So I'm going to go ahead and hide some of this stuff. But basically, I'm going to have 1,000 samples, and I want to show 2 periods. So I'm going to make a bunch of points, starting from a list from 0 to the period times the number of samples. And basically, I'm going to plot a discrete wave, which you can do Desmos by just using it sort of like a point, and then this is basically like a for each type loop. And I have each point here, and then I have 2 pi times the frequency of 2, and then times that point's like value, which is essentially the x value, now divided by z. And the reason we're dividing by z is because if you look over here, you can see that we have a very big interval. When we work with samples, it's going to be array indexing, which means that they're going to be separated at integer intervals, so 0, 1, and 2. And so in order to get the frequency to line up, we have to divide by, we basically have to set the interval to be 1 away from each other. And if I plot the actual sine wave, you can see that they overlap, but I also have to include this over z. So this is basically the sample resolution, and you'll see this in the implementation of the discrete Fourier transform. This is just basically expanding our wave so that points between them are 1 block away from each other, so integer interval. But it's the same frequency, but just instead of using like decimals for x values, we're using integers, which we have to do for array-based indexing. All right, so we see this, and basically now I'm making a list that contains the numbers from 0 to z minus 1. And this is because although I have 2 periods shown, I only want to sample 1 period, which is just z. And then I don't believe this is going to look fantastic, because some of the values, since we have a lot of samples, the peaks are going to be very, very high. Not going to be shown comfortably on this graph. So I plotted the Fourier transforms, and it's called the real and imaginary component. And the real is just the cosine component, and imaginary is just the sine component. If you kind of want some more insight into that, I think the 3 blue 1 brown video is it shows why this is. You can actually think about wrapping this wave up in a circle, and that circle is on the complex plane. But obviously the cosine would represent the real part, and the sine would represent the imaginary part. So that's why it's frequently referred to as real and imaginary. It doesn't really matter for us audio programmers. So anyway, I'm just scaling the result of these down by 200. So that seems to work. And as you can see for the real part, we don't really see anything like any peaks or anything. And I know you're like, well, maybe it's super high up. Well, it's okay. It's supposed to look like this. But when I look at the imaginary part, we see this peak at, what do you know, at 2. Now, what's our frequency? 2, right? So, again, now with a lot more samples, we see how finely we can resolve frequencies using the Fourier Transform. And yeah, again, this is at 2, so we see this frequency of 2 there. But what we're going to do now is just plot the magnitude like I did earlier, because that was just in the imaginary, but we need to consider both the real and imaginary parts, because again, they rule out any issues with phase in sampling. So the magnitude will show us that there is indeed a peak here. But you'll also notice that there's also a peak over here, which is the length minus 2. And it's actually symmetrical about x equals the length over 2. This is the Fourier Transforms, the real part and the imaginary part. And then we can graph this, and this is how we would identify frequencies, is by looking at the magnitudes. And again, I've scaled it down. So this is going to be the very basic foundation in audio programming for finding frequencies, and let's say we're making a pitch shift or an auto tune. We need to see the frequencies first, and once we see the magnitudes of the frequencies, we can see how present they are. We can find, and say auto tune, the first really large peak will be our natural talking pitch, and then that's what we will base our pitch shifting on for the auto tune, as an example. But really, a lot of spectral analysis and resynthesis is going to come from the Fourier Transform, and looking at these frequencies and analyzing them, and then doing stuff with that information. And so finally, we're going to look at the inverse Fourier Transform, which I've also done discrete because I can't really, Desmos is not being nice with supporting graphing the actual continuous Fourier Transforms. But that's okay. This is going to be basically the same thing. We have a sample resolution of 1 over the length, which is z, and then we have numbers 0 to z minus 1. And again, here's just for reference the plotted wave. But the point of the inverse Fourier Transform is that we can actually reconstruct the original wave based on the Fourier Transform. It's a 1-to-1 mapping. So basically this wave, I'm just emphasizing that it has a frequency of 3. I'm not explicitly putting that anywhere. It has a frequency of 3 and a phase of 1. All right, and so we can graph the real and imaginary components, which I believe were already graphed. So this is the real part and the imaginary part. And then we can see that at 3 we have a peak here, and again we have that symmetry going on there. But the important thing is that we'll be working with the first half of the frequencies only. So because it's symmetrical, there's no need to look at the other side because we already know what's there. It's symmetrical. So we'll be only working with the first half. And as you can see, this is the magnitudes, but independently, like these are the real and imaginary components. So now we just need to get these back. So how is this even possible, right? How can we go back to a wave? Specifically, how do we go back to this wave from these two pieces of information? And the answer is, you got to think about what we got. We have the presence of the sine wave at each particular frequency, and we have the presence of the cosine wave at each particular frequency. And because it works regardless of the phase, the only reason that is because of the special identity cosine squared plus sine squared equals 1. But the values themselves are going to change with the phase. As we saw, when I changed the phase, the values change a little bit on the Fourier transform. Let's not do that one, let's do this one. When I change the phase, you can see that values do move a little bit. They do shift around. And that's because it's true that the values will change. Like the presence of the sine wave will appear to be less when the phase is particular, but the peaks will still be at the frequency that's found. And so what that means is that we also have the information of the phase. And by the way, we can find the phase by taking the arctangent of the imaginary and real components. Because again, that's just literally the presence of the sine and literal presence of the cosine of the wave, which is the definition of tangent in the first place. And so, in the inverse Fourier transform, we're just taking each frequency and we're just looking at the amount of sine and amount of cosine present, and we're using that to determine what point should go where for this particular frequency. Based on the sine and cosine information, we have the ability to reconstruct a wave. Which kind of makes sense because when we did it the first time, obviously we had the information by sampling both the sine and the cosine wave. So we can just undo that essentially and get what we had back. Now the last thing is at the end, the Fourier transform, specifically the inverse part, you're supposed to, it depends, you can divide by the number of samples before or after, or you can divide by the square root of n both times. I haven't found an answer in plain English that I'm content with telling you is correct. I just haven't found it yet, and I can't think of particularly where you get a factor of the square root of n each time, or if there's only one time where you get a factor of n. I've seen some stuff, but I'm not convinced yet. So if anybody has any insight on that, that's nice, but it doesn't really matter for us. We just need to remember to divide by it. And one more thing, something that I glossed over initially, is that when we do the Fourier transform, we're actually here using positive 2 pi here. When you think about what is happening with the Fourier transform, we're kind of going from left to right. To undo that, when we do the inverse Fourier transform, in order to retain everything correctly, we need to go from right to left, which means that we would multiply everything in our input by negative because we're going the opposite direction. And so that's why when you look at here, right, so I am collecting the Fourier transform, this is the real part of it, and the imaginary part here. I'm using a negative because this is convention. Again, I haven't found a great reason why we use negative by convention for the Fourier transform, or why we start by going backwards, essentially. I've seen some stuff, but again, not enough to tell you guys in plain English why that is. But it doesn't matter when you calculate it. When you revert back to the original, you will find that it is the same exact way. So you can either start with a negative and then use positive, or start positive and then use negative in the inverse. As long as you use the opposite one in the inverse Fourier transform, you're good to go. And so that's why I have a positive 2 pi frequency here. And I'm just doing the exact same thing. However, is something important to note here. When we look at this real part, right, it's just the sum, right, not an integral. It is the sum from 1 to z, and then again we're indexing by k, it's an integer. But when we do the forward transform, I'm only thinking about, for the real component, the cosine part, and I'm only thinking about the sine part. Well, when we do the inverse transform, I'm actually subtracting the sine component. And notice that I'm also only doing one of these here. And the reason is because the Fourier transform takes you from a wave to the sine and cosine presences, and then the inverse will take you back to the wave. Now, technically, you could think of these, albeit weird, of being essentially the same thing. They both indicate the amount of sine and cosine. And by both, I mean the input wave, the sample wave you're using, represents the amount of sine and cosine, you could argue. And as well as, obviously, the Fourier transform, that which we know represents the sine and cosine. But here's the catch. You can think about your wave as being only they're all real numbers, so it's only a cosine component. Whereas when you do the Fourier transform, you have both that cosine amount and the sine amount. So really, the forward Fourier transform, this formula is still the same, it's just that your sample wave has no imaginary or no sine components built in. Otherwise, you would be sending in two different waves that represented both the sine and cosine components. But you're just sending your wave that is all real numbers, and so there is no, you can think of the sine component. So this formula, although it looks a little bit different from the real one, which is right here, it's essentially the same because when you would, let's say, do the imaginary part, there is no imaginary part. It's actually all zero. And that's what a lot of Fourier transform algorithms actually do, is they just set this, they use the same function, but the imaginary part for the input sample wave is just zero. It's all zeros. And so this gets rid of this entire term because there is no value. And so that's basically it. And if I were to do this with the imaginaries, we would actually find that everything that came back in the imaginary part of the inverse transform would be zero, because we started out with something that was completely real and no imaginary. And so the inverse Fourier transform would send us back something that was completely real and no imaginary. And so, if I plot this, voila, you can see that it contains the exact initial wave that we started with, and we can do this by checking with this actual sine wave with 3 and frequency of 3 and phase of 1. And so that's how powerful this tool is, because now we have the ability not only to analyze frequencies, but resynthesize them. Or if we modify them, we know what we need to do and then resynthesize to produce an output wave. So this is a very, very, very basic introduction to the Fourier transforms. From an audio programmer perspective, I'm not a math genius by any means. I'm just showing you what really helped me at least get the fundamentals for beginning to implement a Fourier transform function. And I'd like to implement a discrete Fourier transform function, but also we can look into the fast Fourier transform functions, and there are a couple different versions of those. Because obviously performance is paramount when we implement these, and the discrete Fourier transform is essentially a double sum, because this is for every particular frequency of WT, right? It doesn't look like it in Desmos, but this is a double sum because for each of these we're doing a sum from 1 to z, and then from each of WT, well, that's a list of 0 to z, or 1 to z essentially. So it is a double sum. So it is O of n squared, which is not very ideal for real-time processing which is pretty much almost exclusively what we use them for in audio programming. So next time we'll start work on the discrete Fourier transform algorithm. And yeah, thank you for watching. I hope you learned something. I hope you liked it. And if you have any comments or critiques, then definitely leave a comment. And yeah, thank you for watching.